Good morning. So in this video, I would like to spend a little time going over the chemistry final study guide and taking a look at basically we're going to be going over the three different ELs that are in this chemistry final, and that would be atomic structure, trends of the periodic table, and chemical reactions. So in the first part here, we're looking at trying to determine the number of protons, electrons, and neutrons in a couple atoms. And so what you'll want to do is you'll want to pull out your periodic table, because that's what we use to determine those things. So the number of protons is the atomic number. So that is the number that is the largest number, or the number that's on the top, and how they are arranged on the periodic table. So if you're looking for, say, lithium, you'll just look for Li on the periodic table, and then the atomic number is the number of protons. Now, if it's a neutral atom, the number of protons is going to equal the number of electrons. And so in this case, the number, lithium is 3 as protons, and then the electrons should also be 3. And the same thing with, say, aluminum is 13 on the periodic table. So the number of electrons is 13. So the atomic number is the same as the number of electrons if it's a neutral atom. We'll talk about ions later. But for right now, those two numbers are the same thing. And then the number of neutrons, remember, to find that, I need to look at the mass, which is also on the periodic table. That's usually the number at the bottom, or it could also, it's going to be a decimal, but that is the other number that's on that periodic table tile. And what I want to do is I want to take that mass number, subtract the number of protons, and that'll give me the number of neutrons. So those are then how I determine the number of protons, the number of electrons, and the number of neutrons. So how do you determine the mass number? The mass number is, I can look that up on the periodic table, and the atomic mass then is the number of protons and the number of neutrons combined. So those are the only two parts of an atom that have mass. So if I want to get the total mass of an atom, I need to add the number of protons added to the number of neutrons. So what are the three subatomic parts? Well, they're the protons, the electron, and the neutron. The proton and the neutron are inside of the nucleus, while the electron is in the electron shell, or the cloud around the nucleus. And so when I look at those three parts, again, the proton is in the nucleus, and it has a positive charge. It has a mass of 1 atomic mass unit. The electron is in the electron cloud, or the shells around that nucleus. It has a negative electrical charge, but it doesn't have any mass. Now, the mass is extremely small, but for our purposes, we just say it's 0. And then the neutron is also in the nucleus along with the proton. It does not have any charge. It has a neutral charge, and there's its mass is 1 atomic mass unit. And so let's go ahead and fill out the chart below here. Then I give you several elements. You'll need to look up the atomic number on the periodic table. So again, just find the element on the periodic table, and the atomic number is how it's arranged. The atomic mass will also be on the periodic table. And again, that's typically going to be a decimal. And then the protons is going to be the same thing as the atomic number. So those are going to be the same. In order to find the neutron, I need to take the atomic mass minus the number of protons, and that'll give me the number of neutrons. And I want to round that number to the nearest whole number. because you can't have a half of a neutron or a quarter of a neutron or 0.6 of a neutron. You need to have a full neutron. So make sure you round those numbers to the nearest whole number when you do the math here. And then, as I mentioned, we're dealing with neutral atoms. So the number of electrons is going to be the same as the number of protons. So all three of those values are going to be the same number, because the atomic number is the number of protons, and in a neutral atom, the number of protons is the same as the number of electrons. So all three of those are going to be the same. Let's define what a valence electron is then. So a valence electron are the electrons that are in that outermost shell. And those are important because a valence electron are the electrons which are involved in chemical reactions. So when we get to chemical reactions, all we really care about are those valence electrons. And then we talked about ionic bonding and covalent bonding. And in ionic bond, you have metals that are transferring their electrons over to nonmetals. In a covalent bond, you have a nonmetal sharing its electrons with a nonmetal. And so on the example here, I have a metal and a nonmetal, so that's going to be an ionic bond. Here I have a nonmetal and a nonmetal, so that's going to be a covalent bond. Here I have a metal and a nonmetal, so that's going to be an ionic bond. And then if I have a nonmetal and a nonmetal, that's going to be a covalent bond. So then I wanted you to practice a little bit with drawing some Bohr models and Lewis dot structures. So here I have nitrogen, and so nitrogen is in group 5, so it's in the fifth column of that. So it's going to have 5 valence electrons. So for the Lewis dot structure, I want to put 5 dots around it. And it has 7 protons and 7 neutrons. So for the Bohr model, I'll put that in the center. And I want to put then 7 electrons around it. So 1, 2, and then that shell is full because that first shell can only hold 2. And then the next 5 I want to put in the outermost shell, or the valence shell here. So 1, 2, 3, 4, 5. Make sure that you're doubling up only after you've gone all the way around. So it'd be like 1, 2, 3, 4, 5, like that. So like on chlorine over here, it's atomic number 17. And so again, I have 17 electrons around it. So that would be 1, 2, 3 shells, and only 7 in the outermost shell of chlorine. And then the next ones, if you just want to check your answers on that, they follow the same rules. But remember, the first shell can hold 2, the next shell can hold 8, third shell can hold 8, and then the next shell, can hold more than that. But we're only going to go to 20 would be the largest that we will ask examples of. But make sure you're doing singles first and then doubles. So both of these elements are in the second column, so they're each going to have 2 electrons in their valence shell. So there, for them, that Lewis dot structure is very similar. And that's just important to note, because they're going to share a lot of chemical properties, because they're going to react with other chemicals in a similar way, because they have the same number of valence electrons. Okay. On the next one, again, we're just filling out some information. So the number of protons is going to be the atomic number. So I just need to look up the element on the periodic table to find the atomic number. The number of protons is going to be the same as the number of electrons. The valence electrons are going to be the same as the group number, so whatever group that's in. And then I'll need to look to see, you know, on my periodic table, then is it a metal or a non-metal? Because if it's a metal, it's going to lose its electrons because it's easier to lose one than to gain 7 in order to become stable. So it's going to lose its electrons. And so when it loses a negatively charged electron, it forms a positive ion. We call those cations. If I look, say, at chlorine, chlorine is in group 7, so it's going to have 7 valence electrons, so it's easier to gain 1 electron. And when it gains a negatively charged electron, it forms a negative ion, which we call an anion. And then, with 6 valence electron, it's going to gain 2, so it's going to form, a -2 anion. Now, neon is already at 5, so it already has a full valence shell. So it's not going to gain or lose. It's not going to form a charge. It's already where it wants to be. It's a noble gas. It doesn't want to associate with anything. It is already full. Okay, so on this next part, we were talking about forming some ionic bonds. And what I wanted you to do here is work through these steps. And so, we're going to put the symbol first, and then we're going to do the Lewis dot structure, which is the valence electrons. And then we're going to show an arrow where that is transferring its electrons from one to the other. So you can see here potassium is transferring its electron over to iodine. And so that potassium becomes a positively charged ion, where the iodine becomes a negatively charged ion. So it forms that ionic bond between that potassium iodine. Next one is beryllium and nitrogen. So beryllium has 2 valence electrons. So it wants to lose those. So it's going to form a 2 positive ion. And then the nitrogen, it has 3 of the electrons are not paired up. So it wants to gain 3. So it wants to form a 3 negative ion. So I can kind of use my crisscross method here, where in order to get that into a balanced molecule, so the ionic charges are balanced, where I have beryllium 3 and nitrogen 2. So I have 3 beryllium atoms and 2 nitrogen atoms that make up that molecule. And then the last one is calcium and chlorine. So again, the calcium is losing electrons, so it forms a positive ion. The chlorine is gaining electrons, so it forms a negative ion. And, then we form calcium chloride molecule, ionic compound over here. Okay, on the next one, we're kind of continuing on with that. So the chemical formula for this would be Na3AS. And the chemical formula for this would be B2SE3, because remember, the group number is the easiest way to kind of determine what the ionic charge of those is going to be. I find it easy to use the chart that I had you put into your science notebook. Let me see if I can find that real quick. I find that's the easiest thing to use in order to find those. And so, this should be in your science notebook, and I can use that to find my ionic charges. In fact, I used it to do this page. And I just find that that's real simple. So remember, the metals are going to form those positive, have a positive ionic charge. The non-metals are going to have that negative ionic charge. And then the noble gases don't have any charge at all because they're already full at that level. Describe the difference between a group and a period. Remember, a group are the columns. Those are going up and down, and those are the same as the number of valence electrons. And then the period are the rows. Those are the same as the number of energy levels or orbits or shells or whatever you want to call those. An atom is basically the smallest unit of matter. And the definition of an element is it's the substance that cannot be divided into a simpler substance. And so that's how we arrange things on the periodic table, is by elements. So it's called the periodic table of elements. So pretty simple there. Describe the trick for identifying the number of valence electrons. I find the easiest thing to do is just look up the group number. So those are at the columns of the periodic table, and so those should be numbered on your periodic table. And so just look at the column number and you're good as gold. How many valence electrons do elements need to be happy, or I think I described it better as being stable. So they need to have a full valence shell for those to be stable. So an example would be that first shell can hold 2, and then the next shell is going to hold 8 after that. When you get beyond that, it does start to get bigger, but all we're focusing on are the first 20. So 8's the magic number. So let's talk about reactivity. And so remember when we talked about the different families in the periodic table, the families that are most reactive are the ones that are out on the edges. So like 1 and 2, group 1 and 2 are very reactive. 6 and 7 are very reactive. Those are the most reactive. The ones that are least reactive are the ones that are inside of the periodic table. So that would be groups, 3 and 4 are not as reactive as those ones on the outside. So as you get closer to the center, those are the least reactive. Some of the trends as far as like the size of the atom or the radius or radii of an atom. As I go down the periodic table, I'm adding energy levels, so they're getting larger as I go down the periodic table. As I move over on the periodic table, they actually get smaller because I'm adding more electrons as I move over. And so there has a greater electrical charge. And so that, think of like a magnet. So those electrons are being pulled to the inside of that positively charged protons, on the inside. So it's being pulled closer until it jumps up in energy level. So, it's like this. And then as they get more and more electrons, it comes down and down and down. And then when it jumps up to the next period or the next row, it bumps up again. So as I move across, they get smaller. As I move down, they get larger. And so on this periodic table, I wanted you to just label the following things. So I have my valence electrons, which are the same as the group number. I have my metals over here who want to lose electrons. And when they lose electrons, they form positive charges. So +1, +2, +3. My non-metals over here want to gain. And so that would be, these are going to group 5 is going to gain 3 to get to 8. So it has a -3, -2, and -1 in order to get to 8. The energy levels are over here on the periods. So those are the rows. So there are 7 periods, just like there are 7 periods in the school day. The trend in the radii, I went over up here, so I didn't put it on my graph here. But basically, again, as I go down, they get larger. As I go over, they get smaller. And the blue, it's kind of hard to see on this picture. Maybe it's easier to see on yours. But the metal are basically everything on to the left of the periodic table, and non-metals are on the right. And then the metalloids are these things that are kind of stuck in the middle. As far as the conservation of mass, that basically states that atoms cannot be created or destroyed in a chemical reaction. On the next part, the mass of my reactants must equal the mass of my product. So if I have 5 plus 5, that gives me 10 on the product side. The number of atoms on the reactant side must equal the number of atoms on the product side. So we practiced a lot as far as counting atoms, and so make sure you know how to count atoms, and then for it to be balanced, the number of atoms of each of those specific elements must be the same on the reactant side as the product side for that to be balanced. And so here I have my reactant side over here. Then on the other side of my arrow, I have my products. That arrow we will often say is yields or reacts to produce the product. So those reactants react to produce the product. And then the subscript is the small number that applies only to that atom, that oxygen atom. And the coefficient, though, applies to the entire molecule. So, for example, in this example, the magnesium, there are 2 magnesiums over here. And then this 2 applies to that entire molecule. So there would be 2 magnesiums there. There are 2 oxygens here because of the subscript. And there are also 2 oxygens on the product side because that 2, again, applies to the entire molecule. So the magnesium and the oxygen. So down here, I want to just kind of count the number of atoms. So I have aluminum. There are 2 of those, and there are 2 nitrogens on the reactant side. And then when I compare that to the product side, that 2 applies to the entire molecule. So there are also 2 aluminum and 2 nitrogen. So yes, that is balanced. Down here, I have potassium and iodine, and I'm combining that with chlorine. So there's 1 potassium, 1 iodine, but 2 chlorine. And over here, I have 2 potassium, 2 chlorine, because again, that 2 applies to the entire molecule, and 2 iodine. So that one is not balanced. So looking at this equation, there are 8 carbon, 10 hydrogen, 2 nitrogen, and 2 oxygen in that large molecule. It's a big one there. And then we also need to talk about the differences between physical and chemical changes. So a change in appearance would be a physical change. So some examples that we talked about in that would be like cutting grass, chopping wood, breaking something into smaller pieces. That's a physical change. We also talked about, a phase change. So like water boiling and turning it into a vapor or a gas, that's a phase change. It's still water. Or ice, so water turning into a solid, that's still water, it's just frozen into a solid. So those are just physical changes. For a chemical change to happen, I need to break the chemical bonds holding that molecule together and then reform those into something new, a new substance. That is a chemical change. And so things that I could look for that show as evidence of a chemical change would be things like, bubbling because a gas is being produced, fizzing, change in color, change in temperature. It can get hot or cold. Those are all examples of evidence of chemical change. And we saw a lot of those in the lab that we did. And then just some simple review questions. So every element has its own atomic number. The atomic number is the number of protons in the nucleus. And in an atom, the electrons travel outside and around the nucleus. The maximum number of electrons in that second energy level is 8. How many valence electrons does an element have? If it's hydrogen, it can have 2 because that first shell can hold 2. The next shells can hold 8. So 8 is the magic number to remember. How many dots are shown in the Bohr model of calcium? The atomic number is 20. So there would be 20 electrons if in the outermost shell. So I went ahead and diagrammed that for you in that Bohr model if you wanted to see an example of that. Sulfur has 16 electrons in the atom. How many energy levels did that electron have? And draw a picture of it. So the valence electrons are what we want to draw. And so it's going to have 1, 2, 3, 4, 5, 6. So it's in the 6th column of, so 6th group. So it's going to have 6 valence electrons on there. Oxygen is going to bond with another element. To be happy, it needs to bond with 1 magnesium would be enough to be able to form a good ionic bond with that. And then this one is asking about, so has the same number of valences. So I want to find that in the periodic table, and I want to find something in the same group because of what it's asking for are the valence electrons. And remember, the valence electrons are the group number for that. So this example, I probably shouldn't be, I know I won't on the test ask about something that's not in the first 20 elements, so I'm surprised that that's on there. But if you have any questions about the study guide, please just shoot me an email and I'll get back to you as soon as I can. I hope that this video was useful to you.